Okay, this is chapter 9, day 12. Chapter 9 is really long. It involves two types of tests. A test for a single mean, often called a t-test, and a test for a single proportion, which is often called on Texas Instruments 1 prop z test. Okay, so tests for means and proportions. There's a third type of test that we're going to run too, and that's called a matched pair. A matched pair is really just a single mean test or a t-test. But it may look like a double mean test, which is actually the next chapter. Initially, it may look like that. A paired test is when there's a single person or single thing doing something twice, and you're actually not interested in the two separate lists. What you're really interested in is the difference between the two lists, which is just one list, and you're going to compare that to 0. 0 represents that there is no change, there is nothing different, etc. So again, we're going to have 3 tests this chapter. We're going to do 2 matched pairs tests, and we're going to do 1 just regular mean test, a t-test, and 1 proportion test. Okay, to practice this. All right, and this is hard to follow. There's a lot here. And you can run a test or you can run an interval on these. You don't have to do both. And then you have type 1 and type 2 errors and some of those things involved. There's quite a bit in this particular chapter. Highly tested area. Okay, so right hand versus left hand strength. Since most people are right-handed, a company that designs machinery has traditionally placed the controls that demand the most hand strengths so they will be used by the right hand. The company decides that it should test its assumption that the right hand of a right-handed adult tends to be stronger than the left. 9 right-handed adults are randomly selected from employees from this company for the test. Hand strength is measured by using a calibrated hand gripper. Okay? It is reasonable to assume that the differences in people's right and left hand is normal. So they're telling us it's normal. That gets us off the hook in the requirements. The people test their left hand first and then their right hand. The hand strengths in kilograms for each person in the summary statistics are given below. So you have the right hand strength averages 11.8, the left hand is 10.9, and then you have the standard deviation of the right hand, the left hand, and then the standard deviation of the right hand minus the left hand. And so the question ultimately is this a test where you're going to compare 2 different things, or is this really a matched pairs test? And indeed, this is a matched pairs test. So we really don't care about the individual lists. What we care about is this list right here, the list of the difference between them, okay? And luckily for us, in this particular case, this is what we're interested in, okay? Right hand minus left hand, okay? So the difference is 0.9, okay? The standard deviation is 0.5, and the variance we really don't need. That's just the square of the standard deviation. So we really just need 0.9 and 0.5. And we're wondering, is 0.9 significantly different from 0? 0 represents there is no difference. In all matched pairs tests, HO and HA, the reference number is 0, okay? All right, so let's slide down and start checking this out. All right, now here's the question. Do these data support the conclusion that the right hand of right-handed adults tends to be stronger than the left hand? Given appropriate statistical justification, briefly discuss any concerns you have about the design of this study. All right, and there is a concern about the design. It's a really cool question. Okay, so we're going to do a matched pairs test. This is going to be HOHA, okay? And when you write mu, please write a sub difference. Mu sub difference is 0, and mu sub difference is greater than 0. And then write what it means. What this means is there is no difference. 0 represents no difference. And then greater than means the right hand is stronger than the left. Remember, there's 3 symbols you can put in there. Greater than, less than, or not equal to. And the context of the problem is going to give it away. Okay, our assumptions. This is the SPIN acronym, okay? Assuming we have a representative sample of right-handed people, okay? We're assuming the population is at least 90 right-handed people. Obviously, there's millions, or in this company, maybe there's hopefully more than 90. Each person's hand strength is independent. That's the I in SPIN. And the N in SPIN, I'm going to write that right here, S-P-I-N, to remember that. Representative sample, population, the 10% rule, the population is 10 times bigger than the sample size. Each hand strength is independent. And then N is sample size. We don't have 30 samples, but normality was stated in the prompt as something you can assume. So we're good to go, okay? Now, I'm going to draw this out over here, okay? I'm going to draw the distribution. I didn't write it up. So what you're going to do in the test part, okay, is you're going to draw this out, okay? 0 goes right here because 0 represents no difference, and that's the assumption that you're making until you prove otherwise, okay? 0.922 was the basic difference. I think 0.9 was the rounded number in the table, but it's actually 0.922. And the standard deviation is 0.5 over the square root of 9. Okay? Now, what you're going to do is you will end up, let's see here, hold on a second. You can go ahead and punch all of this in on your calculator. So I'm going to do that now, okay? So on the calculator, we're going to do stat tests. And I know I have it drawn over that. Hopefully you can see it. T-test, okay? And you're going to type in the null hypothesis, which is 0. You're going to type in the X bar, which is 0.922. You could also use 0.9 because that was the number that was in the table. I went and calculated everything on there. 0.5 was the standard deviation, and N was 9, and we want greater than. And I'm going to go ahead and draw this and see what it looks like. Okay? Now, what you end up having there is a t-score of 5.53 and a p-value. This is in scientific notation. This is 0.0003, and then the t-score is 5.53. Now, how did I get that t-score? That is 0.922 minus 0 divided by the standard deviation of 0.5 over the square root of 9. It's pretty nice that it does it for you. I'm going to go ahead and get rid of the graphic calculator, and then you can see it. Okay, so there is all of my calculations, okay? And then you get that particular p-value, okay? That's a very small p-value, okay? That's from the calculator. All right, now we know that that is almost 0. And you should know the meaning of a p-value. The p-value means, the p-value assumes HO is true. So in this case, there is a 0.03% chance that we would get data this extreme even if HO is true. So it's not likely. So your conclusion is going to be to reject HO and to accept HA as probably truth. So let's look at that. Okay? So I wrote that here. If a p-value of 0.03, we have sufficient evidence to conclude that the right hand is stronger than the left. Most of the time, people start with this sentence frame. Reject HO at alpha 0.01. I could have picked 0.05, I could have picked 0.10, whatever, but I just chose 0.01. It doesn't matter, it's smaller than all of them anyways. Okay, the concerns question. Okay, one of the concerns is the lack of randomization in the experiment. If you notice, everyone, I think, did their left first, then their right. And sometimes when you do that, you sort of learn what to do, and then the right hand's a little bit more efficient. So they should have randomized which one went first. There's a lack of randomization in this prompt. Okay? Okay, now, this problem could have also been done with a confidence interval instead of a test. I'm not going to do that here, but I am going to be doing confidence intervals in the next 3 prompts as well. One other note, when you have a p-value that's low, you are running the risk of a type 1 error, because type 1 error is you rejected HO, but HO could have been true, and you'll find that out later. But the consequences of that in this case, I don't really know what it would be for the company. Maybe that they implement all these new ways of having their employees do work and it didn't make any difference, something like that. But this is the risk of a type 1 error, which is something else you should be familiar with, okay? All right, the next prompt is another manual dexterity problem. And this has a rather long opening prompt here, okay? And this is the developers of a training program designed to improve manual dexterity claim that people who complete the 6-week program will increase their manual dexterity. A sample of 12 people enrolled in the training program. A measure of each person's dexterity on a scale of 1 to 9 was recorded before the start of and just after the completion. So here we go. Okay, you have 2 different lists. And when you see this, especially when you're done learning the course, the question becomes, is this 2 separate samples, or are these samples somehow paired up? Well, the answer is they're paired up. Okay, this is the same person doing something twice. So this is paired data. So this would be a paired t-test, often called a matched pairs. Okay, either way is fine. Okay, so I'm going to have to move up and get rid of all this data, but you see this on your sheets, okay? And the question is, can you conclude that the mean manual dexterity for people who have completed the 6-week training program has significantly increased? Support your conclusion with appropriate statistical data. Fine. I'm going to do this one as a t-test and as a confidence interval. You would never do both on the test, but just to see that you do have the options, you'll be able to review some of the stuff from the previous chapter. Okay, here we go. Okay, here we go. So the first thing you're going to do is you're going to write your HOHA. And your HOHA is, again, this is a matched pair, so I'm going to use mu sub difference is 0. 0 represents that there is no difference. The training program didn't work. Okay? Training does not improve dexterity. HA is that we do have a detectable increase. A detectable increase means greater than 0, meaning the training does improve dexterity. Okay? Here's our assumptions. And again, the acronym to memorize is SPIN. Although you wouldn't write that out. Okay? Assumptions are we have a representative of all people in the company, even though we only have, I think, 12 of them. The assumptions are that there's at least 120 people working in the company, okay? Every person's dexterity is independent, and this is tricky. The sample size is not very large. It's not bigger than 30, so we cannot invoke the central limit theorem. Another problem is the data of the difference doesn't make a very good box plot. And I'm going to show you this, okay? You should, if the data is less than 30 and you have it, you should draw the box plot out. It's not terrible, but it's definitely not great. So let me show you what I did here, okay? So what I did is I typed all the data in L1 and L2. I put the after program in L1 and the before program in L2 because an improvement would be measured by subtracting the after program minus the before. And these are those numbers right here. These are the differences. And if you notice, most of those differences are positive. So it looks like the program probably worked. There's a negative. A negative number represents that the program didn't work for that person. So for only 2 of the 12 people did the program not work for them. And then this last person, the program had no effect. But in general, it looks like there is an effect, okay? So what I did is I went second y equals, and I made a box plot of L3, because that's what I'm interested in. I clicked zoom 9, and then you notice that the box plot isn't perfectly dated. This is the 0 line right here. So this it's a little bit skewed to the right, but it's not terrible. But in general, I think I like what I wrote here when I said, go ahead and proceed with caution on this because we may not have normal data, and that's okay. So what you would do is you would draw that box plot how I had it, okay, and just kind of point that out, okay? Now I'm going to draw the curve up here, okay, and then I'm going to do it on the calculator again. I'm going to move it over here. So to do this, you want to draw the curve, okay? I would put that with this. And 0 goes in the middle. Whatever is an HO goes right there. So that goes there, okay? Then the X bar of 0.375, which you can see listed right there, that is the typical increase in dexterity. It's about 0.375. And the standard deviation was 0.367, and we're going to divide by that by the sample size, the square root of 12. And then I'm going to go ahead and do this in the calculator. To get this t-score right here, what you do is you go 0.375 minus 0 divided by this standard deviation, 0.367 over the square root of 12. And that's going to come out 3.58. And 3.58 is very big. Remember, over 3 is considered unusual. And then the p-value is going to come out 0.0023, okay? And that's going to barely be on that curve. So if you wanted to do it by hand, this would be how you do it. You would do NCDF and then 3.58 comma infinity, right? That's how you would do this by hand. And you want to write this out as if you did it by hand. But most likely, you're going to go to the calculator, and let me do that now. So I'm going to erase this. Okay, I'm going to go to the calculator, and I'm going to type that data in. Stat, tests, whoops, stat, tests, and I'm going to go to t-test, okay? And on t-test, 0 is going to stay there. I'm going to type in 0.375 because that was my average increase in manual dexterity. 0.367 is the standard deviation, and the sample size was 12. And greater than we're going to leave. And I really like to do draw so they can draw it out. And as you can see there, that quickly does the t-score and the p-value for you. You could do it by hand, like I showed you, or you could go to your calculator and shortcut it a little bit. Okay? All right. Clear that. Great. Now, what we're going to do next here is we're going to do our conclusion. And our conclusion is going to be, can you conclude there's an increase? Yes. We're going to, probably the first thing you're going to write is reject HO at alpha 0.01 because the p-value is less than alpha. That's a good little opening sentence. Yes, we can conclude that the training program is effective in increasing manual dexterity. We reject H at 0.01, but the p-value of this, we have sufficient evidence that the training program works. Okay, there's lots of ways to write this, but that's the idea. Now, let me show you another way you could have done this, okay? Another way you could have done this whole problem were to be using a confidence interval. You could have done it this way, okay? And how it would work is instead of running the test, you would do a confidence interval, and the confidence interval, if you recall, is x bar plus or minus t star times s over the square root of n. And if you did that, you would get 0.375 plus or minus. Now t star is going to come from the chart. The sample size is 12. You're going to subtract 1, make it 11, so your degrees of freedom is 11. So I'm going to do a 98% confidence interval. The reason I'm going to do a 98% confidence interval, recall this, is because my alpha's 0.1, and this is a one-sided test, meaning it's greater than. There are two types of one-sided tests, greater than and less than. The two-sided test is not equal to. This is a one-sided test, a greater than test. Look at HA, okay? And I'm gonna double that, make it 0.2, and then subtract from 100, I got 98%. So 98% is my confidence level. My degrees of freedom is 11. On that chart, that number is gonna come out 2.718, okay? And then my standard deviation for this whole thing is going to be 0.367 divided by the square root of 12, okay? And then if you get that, let's go ahead and go to the calculator and let's see if we can figure this one out, okay? So let's do it. So I'm going to go stacked tests, and I'm going to go, like last chapter, I'm going to go to T interval, which is, I believe, item number 8 on the calculator, okay? And I'm going to go ahead and type in 0.375 was the mean. The standard deviation is 0.367. And then the sample size was 12, and it's 98% confident. And if you calculate that, you get between 0.09 maybe, 0.9 all around to, and 0.66. 0.9 and 0.66, okay? So you get to 0.09 and 0.66. All right, now, with that, when you have it like that, what you're looking for is 0 in the interval or not. 0 is not in the interval. The whole interval is greater than 0. That's why you can conclude that there is sufficient evidence that the training program works. How you would write it, you would say 0 is not in the interval. The whole interval is larger than 0. Therefore, we have sufficient evidence that the training program works. Okay, let's go on to the next problem. And again, with a reject HO, you are running the risk of a type 1 error. Okay, and a type 1 error would be HO is actually true, that the training program doesn't work, but you found that it did. And you may be installing new software or new ideas to help your workers, and it wasn't necessary. Okay? All right. Okay, this next problem is about DUI crashes in the city of Westminster. Okay, so Westminster DUI. All right, it is presumed 20% of all car crashes are alcohol or drug related. That's sad, that's true. In a sample of 100 car crashes in Westminster in 2014, 25 were related to alcohol or drugs. Is there evidence that Westminster's car crashes are higher than 20% justified? All right. First thing you ask yourself, do we got a mean or a proportion? We got a proportion. Is it one sample or two? It's one. So we're going to be doing a one proportion test, which on Texas Instruments is called 1 prop Z test. You could also do an interval for this too and draw a conclusion. Either way is fine. All right. So here we go. You can use the symbol pi or p. I often use the symbol pi here because I really like it when all of the Greek symbols mean the population and all of the Arabic symbols are in our lettering system mean the sample. Okay, so p or pi is 0.2. What does that mean? 20% of Westminster's crashes are alcohol or drug related, just like the rest of the nation. And pi or p is greater than 20%, more than 20%, and we're trying to prove this. Does 25 out of 100 prove for sure that 0.2 is not the right number? 25 out of 100 is only 25% in a very small sample. Let's check it out. Okay, our assumptions are the SPIN acronym. I'm going to write this for the millionth time. Okay, are the SPIN acronym. Okay, S is representative sample. Assume we have a representative sample of Westminster car crashes. Okay, P, assume the population of the car crashes is at least 1,000, which I'm sure it is in any given year. Okay. Each car's sobriety status is independent, okay? And do we have enough samples for a normal curve? We should. N times P, that's greater than 10, that's 20. And then N times 1 minus P is greater than 10, yeah, that's 80. So the CLT, central limit theorem, ensures normality. Awesome. Okay, now, this is our answer. The p-value is going to be this right here, 0.1056. And let's go through how we're gonna draw this out, okay? We've done this so many times. All right, what goes here is 0.2, okay? Which is HO. HO always goes in the middle, okay? It's 0.2. All right, and then over here, we're gonna write 0.2 times 0.8 over the square root of 100, okay? And then our sample, our p hat, is 25 out of 100, which is 0.25, okay? Now to get a z-score and a p-value, we can do it by hand. We can go 0.25 minus 0.2 divided by this particular standard deviation, 0.2, 0.8 over 100, okay? And we're going to get a z-score of 1.25. 1.25 if you do that by hand, okay? Then you're going to go ahead and put that into NCDF. And we want the area above that, okay? And we know the answer is around 10%. I'll shade in 10% already. 1.25 comma infinity, and again type in a number like 100 or 1,000, and you're going to get the answer of 0.10, erase that, try it again here, 0.1056, okay? 0.10, and there's your answer right there. All right, so you can do this all by hand, but of course there is a calculator function, and let me do that now for you, okay? All right. So I'm going to go stat tests, and I'm going to do a 1 prop z test. Okay? And in this case, the p sub null is 0.2. 20% is our anticipated or our assumption of all alcohol and drug-related car crashes. Our sample was 25 out of 100. Not too much bigger than 20%, but is it enough to say we got a bigger problem than the rest of the nation has? Greater than's fine. And we're going to click draw. And there's the answer. That is a quicker way of doing what I wrote out. Now you want to write it out as if you're doing it by hand anyways. So that's how you do that. Okay. Now, the other way you could have handled this is you could have done a confidence interval on this. And a confidence interval is going to be p hat plus or minus z star, okay, times the square root of p hat 1 minus p hat over n, okay? You could have done it that way, and that would have worked out. That would have worked out just as well, okay? And I have that written out here, but I'm going to go ahead and write it up here for you, so you see the whole thing. Okay, all right. Okay, so and when you do this, I actually have a wrong answer here. Let me scratch this out right here. Okay. I'm going to go ahead and do a 95% confidence interval. Okay, I'm going to do a 95 for you. Okay, here's how it works. It's going to be 0.25, because that's our p hat, plus or minus, and if you remember the 95% confidence interval, the z star value, the critical value, is 1.96. And you're going to write in 0.25 0.75 over n, which is 100. Now, it's interesting in the answer key that I had, a lot of people ask, where did the 0.2 and the 0.8 go? That was part of the HOHA, which you still see up there. Well, a confidence interval is a different mechanism of proving things. It doesn't make an initial assumption. What it does is say, give me what you got. All right, we got 25%. And then you can look for your assumption later within the interval to see if it's true. It works a little bit backwards. So this is what you calculate. So I'm going to go ahead and go over to the calculator, and we're going to do that, okay? Okay, stat, tests, and I'm going to go to 1 prop z interval, which is down below here. 1 prop z int. Okay. And I'm typing in 25 over 100, and I did a 95% confidence interval just to do it, okay? And then I'm going to go ahead and hit calculate. Okay, so now that we've done the 95% confidence interval, we think that the percentage of crashes that were alcohol related in Westminster are at the lowest about 16.5% and at the highest about 33%. But the key thing here is that 20% is in the interval. And because it is in there, we're going to fail to reject. That's kind of the key principle of this, because 20% remains a possibility. All right, So let me go ahead and go back to the notes, all right? Okay, and as you can see here, that we're going to fail to reject at alpha 05 because the confidence interval did capture the HO of 0.2. So we have insufficient evidence to conclude that more than 20% of Westminster's car crashes are alcohol drug related. 20% remains a possibility. Okay, now we're going to go on to the last problem, and this is a mean problem. Let me read it to you. LQ versus the national IQ. The IQ for the nation is 100 with a standard deviation of 15. In a random sample of 38 students from La Quinta, it was observed the average was 105.3. I guess we'll assume it's the same standard deviation of 15. Is there evidence based upon this sample that the LQ student body has a higher IQ than the national average? Okay, first thing. HO, mu is 100, HA, mu is greater than 100, because we're thinking that LQ's score is higher. And this is clearly a mean problem, not a proportion problem. Here's our assumptions. Here's our SPIN acronym again. S, we have a representative sample. P, we're assuming we didn't sample more than 10% of the population, meaning the population is at least 380 La Quinta students. I, each LQ score is independent, and then the N. Do we have enough samples to assume normality via the central limit theorem? Yes, we do. The central limit theorem ensures normality because we have more than 30 samples. Okay, so we're set up. Now we're going to go ahead and we are going to do the test, and I'm going to go ahead and write it out, and then we're going to do it on the calculator. So here's a good area to do this right here. So this is what you want to write. You got a raw score, you got a z-score, and you got a percentile. Okay? All right, so here we go. So 100 goes here because that's the presumed mean if our HO is true. Standard deviation's 15 divided by the square root of 38. Okay? Then we are going to have a 105.3 is our X bar. 105.3 is our X bar. So the question is 38 students averaging 105.3, is that good enough to say that we've proven that the whole group is probably over 100? Okay, let's check it out. Okay, so we're going to get a t-score. I shouldn't have wrote z here. This is going to be a t-score because we're doing a mean. Okay, so the t-score I'm going to put right here. The t-score is going to be 105.3 minus 100 divided by the standard deviation of this statistic. And that t-score is, I got it on my sheet here, is 2.18. 2.18. So 2.18. Now we can turn this into a percentile by hand if you want. On your calculator, you can go TCDF if you want and go 2.18 comma some form of infinity, probably the number 100. And then the degrees of freedom is 37, n minus 1. And that's going to get you a p-value of 0.0179, okay? So I'm going to do this on the calculator so you have a sense of it, okay? So you can, if you need to pause this at any time, obviously, and write it down, no problem. So you're probably going to do this via software, so let's check it out. So on the calculator, you're going to go stat, and you're going to go to tests, and you're going to run a t-test, okay? All right, so 100 is HO. X bar is 105.3. And the standard deviation on this was 15. and there were 38 people involved, okay? And we're looking for greater than. So most people will do it this way, and that way it's real easy to get the answer. That's the calculator answer on that. Now, you can do TCDF if you wanted to do it by hand, and that would be second distribution, and I would go to TCDF right here. Most people aren't going to go this direction. They're going to go another way. So I'm going to make the lower bound the z-score of, what was it, it was actually 2.178 was the actual number, literally. And the upper bound is some massive z-score. And the degrees of freedom was 37. We're going to get a similar answer, if not the same. So let's see what we got. There you go. It's the same exact answer. You can do it either way. Okay? All right. So let me move the notes up a little bit, and let's go back through this, okay? So we've gone through most of this. So this was our answer, 2.179. And how do we write the conclusion? We're going to write, we reject HO at alpha 05. I chose 05 basically because this is between 01 and 05, and I want to make the La Quinta kids look good. So I'm saying 05 because that's a reject. We have a p-value of reject because this is smaller than alpha. We have sufficient evidence to conclude that LQ's IQ scores are higher than the national average. If this was 01, then you would fail to reject. You wouldn't have enough evidence. This is between the two most common alpha levels of 01 and 05, and they would say different things based upon how much evidence you want. Okay, now, if I did an alpha level of 05, then if I did the equivalent confidence interval for that, it would be a 90% confidence interval, because this is a one-sided test greater than. So I'm going to double alpha and make it 10%, and then go 100% minus 10%, and I get 90%. So I'm going to cross this one out because I'm using this one right here. So this is my confidence interval, and I'm going to write it out for you bigger. 105.3 plus or minus 1.697. How did I get that number? That is degrees of freedom 37, but the closest number on the formula sheet's 30 at 90%, and that's the number on the chart. And then you're going to multiply that by 15 over the square root of 38. And when you do that, I'm going to go ahead and put this on the calculator, you'll see. And what you're going to notice is 100 is not in the interval. It's slightly higher, meaning that we have evidence that we're slightly better than the nation. So let's go ahead and go over to the calculator and do that. Okay? So stat tests, and I'm going to do a t interval, which is right there, t interval. And there are the numbers, and I'm going to do a 90% interval this time. That's the difference, because again, I use alpha 05. I doubled it because it was a one-sided test. And then I went 100 minus to get my confidence level. I'm going to arrow down to calculate, and we will have it. So there is what I think the whole school will average. I think the whole school will average 101 to 109, slightly more than 100. 100's not in there. So if I were to write my conclusion, I would say reject HO because 100 is not in the interval. The whole interval is higher. We have sufficient evidence to suggest, even ever so slightly, that the average IQ score of an LQ student is higher than the national average. All right, that's the key lesson on Chapter 9. Good luck.